Okay, this video is going to focus on the physical properties of molecular substances. First off, let's define what a molecular substance is, as opposed to something which is not molecular, like perhaps a metal or perhaps an ionic substance, for example. So a molecular substance uh, is going to be composed solely of nonmetals in general. All right, and usually the substance is going to consist of molecules. Now, what the viewer needs to remember is that a molecule has a very specific definition. It's a collection of atoms which are bonded in a specific ratio utilizing covalent bonds. All right, now the model compounds I'm going to focus on this morning are going to be carbon, tetrachloride, and water. Okay, both of these are molecular substances. I want to address the presence of hydrogen in the water because new students, when they look at the periodic table, are going to find the hydrogen in group 1, and if they're watching this video, are going to be looking at this and going, well, how can he say that hydrogen is a non-metal if it's in group 1? And the thing is that hydrogen actually appears essentially in two parts of the periodic table. It has properties that are consistent with group 1A, to be specific about it, and it has properties that are consistent with group 7A. Now, for all applications, essentially, in my view, except for a few, hydrogen is always considered a nonmetal. So when you see it in a compound, in any sort of molecule or chemical formula, you should consider the hydrogen from the aspect of its chemistry to be acting as a nonmetal. All right. So these two compounds represent essentially two kinds of molecular substances. Now, in a previous video, I outlined the idea of heating curves. All right, and a heating curve basically looks at the physical properties of a particular substance as it responds to an input of energy. All right, in other words, we can look at a substance and determine how it responds to an input of energy. So if we look at the heating curve for water, and I'm going to put time of energy input down here on the horizontal axis, all right, and on the vertical axis we're going to have the temperature in degrees centigrade. We're heating this substance at a constant rate of energy input. So you can imagine having, we would start with a beaker of the substance or a dish holding the substance on a stove. All right, here's my substance. Here's the stove. All right, and the stove is set up so that we're heating the substance at a constant rate. And then we just keep track of what's going on with the substance over time as we measure its temperature. And what you're going to see is a curve that's going to look something like this. Just a rough sketch. All right, and this point right here is going to be the melting point of the substance. And I went through all this in the previous video, so I'm not going to go into significant detail here, except to remind the viewer of a few things. So first off, all substances are going to have a melting point. If we start with a solid, for example, eventually we're going to get to the liquid. All right, and to get from the solid to the liquid, we have to melt the substance, and that's what this platform is showing us right here, which is governed by the delta H of fusion for any substance. And then to go from the liquid to the gas, we're going to have a similar situation, another flat plateau where the temperature is not changing, and that plateau is governed by the delta H of vaporization. This is just the energy that has to be put in to drive the substance at a fixed temperature from its liquid state into its gas phase. And by the same token, the delta H of fusion is the amount of energy that has to be driven into the substance to push it from its solid state at a fixed temperature to its liquid state at a fixed temperature. All right, now, both of these substances that I'm utilizing for this discussion of molecular substances go through these transitions. Now, what I want to talk about is the force of attraction between these substances, because when we talked about the heating curves in general, we related metals, ionic substances, and molecular substances. And the thing is that the forces of attraction that occur between, say, metals or between ionic substances are different than the forces of attractions that occur between molecular substances, because in the case of the metals, we're dealing with metallic bonds, and in the case of ionic substances, we're dealing with ionic bonds. In the situation here, though, we're dealing with forces of attraction between molecules. So let's address that issue. If I calculate the molar mass of carbon tetrachloride, all right, it's 153.81 grams per mole. Water, on the other hand, is about 18.016 grams per mole. So you see there's a significant difference in molar mass between these two particles. It's about 8.5 to 1. In other words, the carbon tetrachloride is 8.5 times heavier than the water is. So carbon tetrachloride is a significantly heavier molecule. It has a much bigger molecular volume to it. Now, but for comparison's sake, if we look at the boiling point and the melting point of the two particles, the boiling point of carbon tetrachloride is 76.72 degrees centigrade, and its melting point is minus 22.92 degrees C. For water, the boiling point is 100, and the melting point is 0. So if you compare these values, there's a striking difference between the physical property of water and that of the carbon tetrachloride. Water's boiling point is significantly higher, and its melting point is significantly higher, yet the molecule itself is considerably smaller by comparison to the carbon tetrachloride. So let's talk about what's going on here. And in order to do that, what I want to do is draw the Lewis formulas first for both of the molecules. So for the carbon tetrachloride, we have a tetrahedral structure that's going to look like this. And for the water molecule, we're going to have a structure that looks like this. And there are electrons on the chlorines here. I guess I'll just go around very quickly and try to put them in, get them in here. I don't know how well they're going to show up. All right, now you can see when you look at the two molecules that that they look different, and that's because they have different structures. All right, the carbon tetrachloride is tetrahedral, and the water molecule is actually bent. All right, we call this a bent molecule. And you can see something else about the water. It actually has a top and a bottom. And I'm defining this arbitrarily. You could do it the other way around if you want. It doesn't really matter to me. Whereas the carbon tetrachloride really this represents, it's more like, it operates more like a sphere than it does anything else. So this molecule really does not have a top and a bottom. Then the next thing that we want to address is whether or not these two molecules have polar bonds in them. And the way we do that is by evaluating whether or not there is an electronegativity difference. All right, and electronegativity is a periodic trend. It increases going left to right, and it decreases down any group. The main point is that when two atoms are in a bond, whether or not those two atoms are going to share the electrons equally is going to depend on the two atoms opposing electronegativities. And when we look at the water molecule, oxygen sits far to the right of hydrogen in terms of its electronegativity, and is a lot more electronegative. Oxygen is a lot more electronegative of an atom, so it withdraws electron density towards itself. Right, and I can kind of show that this way. I'll make this bond into an arrow. So the electron density is pulled towards the oxygen. The net result is that there's going to be what we call a negative partial charge on the oxygens, and there's going to be positive partial charges on the hydrogens. In terms of the carbon tetrachloride molecule, there will be a similar issue here in that the Cls are going to be slightly more electronegative than the carbon. So we can go around and put little partial negative charges on the Cls. We can put a little partial positive charge on the C. Now the question becomes, are either one of these molecules polar? And when we define the concept polar, what we mean to say is a molecule that has opposite charges, and I'm going to abbreviate this, opposite charges, on opposite ends, physical ends of the molecule. Are there opposite charges on opposite ends of the molecule? And if there are, the molecule is polar. So the issue is that, and this is the way I would encourage students to look at this issue. Think about if you place the molecule between two charge plates, whether or not the molecule is going to orient itself between those plates. So if we place a molecule between two charge plates, will it orient itself relative to the plates? And the water molecule, when it's placed between these plates, is going to line up like this. It's going to be flipped so that the hydrogens face towards the negative poles and the oxygen is faced towards the positive poles. All right. However, the carbon tetrachloride, and I'm going to draw it like this. The carbon tetrachloride is going to have an infinite number of orientations between the plates. It can turn, it's going to be busily turning any direction that it wants to be in, because there's no place on this molecule where you've got opposite ends on opposite ends of the molecule. So this molecule is going to have random orientations when you place it between two plates that have opposite charges, whereas your water molecule very specifically, is going to be lined up between the plates, so as to place its opposite charges face towards the appropriate opposite charges on the plates. So the water molecule is polar. The carbon tetrachloride molecule is nonpolar. All right? Nonpolar forces are much weaker than polar forces. All right? Much weaker. All right? And coming back up here to my heating curve, just like with metals and with ionic substances, the force that holds the particles together are based on electrostatic forces, right? Electrostatic force. An electrostatic force is just simply the force of attraction between something that's positive and something that's negative. And the issue with molecules is that they operate exactly the same way as the atoms do in a metallic bond or the ions in an ionic bond. However, the forces are much, much weaker. And because of that, their melting points and their boiling points are significantly lower. The last thing I want to say before I close this video is that these forces of attractions in molecular substances are between the molecules. They're between the molecules, not within them, they're between them.